So in our last example, we solved for the force acting on the sidewall of a tank. The question I want to ask now is, what if the side of that tank were on an angle? In other words, instead of having a vertical walled tank like the one we've been playing with, what if we had one where the side were on an angle? In other words, we're looking at this trapezoid. What would the force acting on that wall be? Well, it turns out to be a little bit more complex, but it'll be okay. First thing we want to do is consider that we can still measure the height going down this way. But what we need is some coordinate system that deals with the fact that this wall is on, that was sloppy, but this wall is on an angle theta. And so what we're going to do is we're going to define ourselves a nice little coordinate system that starts at the top and works its way down called y. And instead of looking at the forces all over this thing, let's just deal with a section here in the middle. So maybe this is a door that you're trying to keep shut, or you could extend this to be the whole thing, but it's some block. In other words, we're going to look at a block like this in the middle of the door. Excuse the difficult drawings, but there it is. This isn't a differential area. This is a finite area that, like I said, could be a door or something like that on the side of this strange shaped tank. In fact, if you look at it from the side, what I want to deal with right now is a rectangular door. And so if we were looking at this thing from this angle here, you'd see a rectangle. Well, as we've done in the past, we're going to start with a differential force. And so if we have, say, a little differential area here, we could call this dA, and then acting on it would be our differential force dF. We could write, which we've done before, that the differential force is equal to the pressure times the differential area. And we know, because we've done it 1,000 times now, that the pressure is equal to rho g h dA, where we defined h as this extra coordinate moving down from the surface. And so if we wanted to find the overall reaction force, we would integrate both sides, and we could say that the reaction force Fr is equal to the integral over the area of rho g h dA. In other words, if we integrate this over the whole thing, we're going to discover something like this. That's the reaction force. The challenge we have is that everything's on an angle. And so we need a way to relate this h coordinate to this y coordinate that takes into account the angle. In other words, how far down in terms of y is a given h? Well, this comes from the similar triangles, or, well, just from trig, I suppose, where we can say that the sine of the angle theta is equal to the opposite leg, which is h, divided by the hypotenuse here, which is the y-coordinate, since y is measured along that surface. And what that lets us do is write that the reaction force is equal to the integral over the area of rho g y sine theta dA. So let's work with a, incompressible fluid in a constant gravity field. So we can write rho and g are constants. That lets us pull them out of this integral, which leaves us with the reaction force being equal to rho g sine theta integral over the area of y dA. Now this might look familiar to you. Have you seen this before from your solids courses, maybe dynamics course? This has a name. This is the first moment of inertia. First moment of inertia. And with a little bit of calculus that we're going to skip altogether because you've seen it elsewhere, we can write that that first moment of inertia is equal to oops, that's the sloppiest y I've ever written, is equal to yc times the area, where this yc is the location of the centroid. Centroid location. And so, you may remember, for something like this rectangle, we can write a centroid in the middle of it, right? And that comes up here to our actual area that we're interested in. We can measure the distance along the wall to that centroid as yc. And it is how far below the surface? Well, hc. And so what this means we can do is we can write that for any shape, the reaction force on an inclined surface is rho g sine theta times yc a, where yc is the distance along the surface of the centroid of your shape, or this is equal to rho g hc times the area, where hc is the distance below the surface of your shape. And again, this works for any shape.